You know, from your phone to your car, batteries are kind of the silent heroes of our modern lives, right? But what's the actual magic happening inside that tiny metal can? Well, today we're going to peel back the label and explore the incredible science of electrochemistry.
I mean, seriously, have you ever wondered how a battery actually works? We plug things in, we charge them up, they work, and then, eventually, they die. But the how behind it all is where things get really fascinating. And let me tell you, it's not magic. It's this brilliant dance of atoms and energy, and by the end of this, you'll get exactly how it all happens.
All right, so the secret to all of this, the key that unlocks everything, lies in this one fundamental chemical process. It's called a redox reaction, and believe me, it is the engine that drives every single battery out there. At its heart, electrochemistry is basically the ultimate crossover episode where physics and chemistry team up. It's all about how we can take the energy stored up in chemical bonds and turn it into a flow of electricity we can use, or do the reverse. So this redox reaction, what is it? Okay, imagine a chemical tug-of-war for these tiny little particles called electrons. On one side, you have a substance, the donor, that loses its electrons. We call this oxidation. At the very same time, another substance, the taker, gains those exact electrons. And that's reduction. The key thing to remember is one can't happen without the other. This simple give and take is the source of all the power. So how does this simple reaction actually create power we can use? Well, it all happens inside our first key device, the galvanic cell. Now, this is the classic setup that generates electricity. Think of it as the fundamental blueprint for a battery.
Now take a look at this setup. It's actually pretty cool. We've got two different metals, right? Zinc and copper, and each one is just sitting in a solution of its own salt. Then you see they're connected by a wire up top. That's where the electricity is going to flow. And then there's this weird little U-shaped tube called a salt bridge. Every single part here has a super important job to do.
Okay, so here's the play-by-play of what's happening. First, over at the anode, the zinc metal literally starts giving up its electrons. Step 2, those now free electrons go zipping through that wire, and that flow is our electric current. Third, they arrive at the other side, the cathode, where the copper ions floating in the solution are just waiting to grab them. And finally, step 4, that salt bridge lets other ions move between the two beakers, which is crucial for preventing any charge from building up and stopping the whole show. It keeps the circuit running nice and smooth. And this quote just nails it. The salt bridge is like the unsung hero here. It's the operations team working behind the scenes. Without it, the reaction would stop almost instantly. It's managing all the background logistics, making sure the system stays balanced so those electrons can just keep on flowing.
Okay, but what if you want to make a chemical reaction happen that doesn't want to happen on its own? For that, you need the total opposite of a galvanic cell. You need an electrolytic cell, which actually uses power to force chemistry to do what we want.
Now look closely at this diagram. What's the first thing you spot? That big battery symbol at the top, right? Instead of producing power, this cell is literally plugged into a power source. That external battery is providing the energy, the push, needed to drive a reaction that would never happen otherwise, like splitting molten salt into pure sodium and chlorine gas. Yeah, think of it this way. A galvanic cell is like a waterfall. The energy just flows out naturally, spontaneously. An electrolytic cell, on the other hand, is like a water pump. You have to put energy in to force the process to happen against its natural tendency.
So let's just put them side by side for a second. Galvanic cells, they're spontaneous, they generate energy, and the anode is negative. Electrolytic cells, the exact opposite. They need an energy input for their non-spontaneous reaction, and their anode is positive. It's basically a perfect mirror image of how energy flows.
So we know some reactions are spontaneous and some aren't. But how do we know which is which? How can we actually predict what's going to happen when we pair up two different metals? Well, turns out chemistry has a rulebook for that. Yeah, this is the big question, right? In our zinc-copper cell, why did the zinc give up its electrons and not the other way around? The answer lies in a definitive, a power ranking of the elements. And here it is, the electrochemical series. Whoa! Okay, don't be intimidated by all the numbers. Seriously, just think of this as a league table for elements, ranking them by how badly they want to gain electrons. That ranking is called the standard reduction potential. The higher and more positive the number, the more that element wants to take electrons. The lower and more negative it is, the more it's willing to give them away. And if you look down the list, you can find our players. Copper with a positive value, and zinc way down with a negative one. This table right here holds the secret to predicting the winner. And the rules are actually super simple. You find your two elements on the list. The one with the lower, more negative number, that's going to be your anode. It's the one that loses the electrons. The one with the higher number becomes the cathode. It gains them. And get this, here's the key takeaway for designing batteries. The bigger the difference between those two numbers, the more voltage your battery will produce. This is exactly why certain materials, like lithium, are so valuable for batteries. They create a huge voltage gap when you pair them with the right partners.
All right, so we've got the concepts down. We've got the rule book. Now let's do what scientists do and actually put these numbers to work. We can calculate the exact voltage our zinc-copper cell should produce.
And this simple formula is literally all we need. The total voltage of the cell, its potential, is just the potential of the cathode minus the potential of the anode. So simple, but so powerful.
So let's apply it. We go back to our series and look up the values. Copper has the higher potential, so it's our cathode at positive 0.34 volts. Zinc has the lower one, making it our anode at negative 0.76 volts. Now we just plug them into the formula. 0.34 minus negative 0.76.
And there it is, 1.10 volts. How cool is that? We just calculated the standard voltage of a classic zinc-copper battery just by using the fundamental rules of electrochemistry. See? It's not magic, it's predictable, calculable science.
So why does any of this matter? Well, because understanding these principles lets us do some incredible things. We can design way more powerful and efficient batteries, we can purify metals from raw ore, we can stop bridges from rusting, we can even build advanced fuel cells and medical sensors. This science is literally everywhere.
So the next time you pick up your phone or start your car, you'll know the secret inside isn't magic at all. It's this beautiful, invisible tug of war for electrons. Which leads me to a final question for you. Now that you can see it, what other hidden chemical reactions do you think are powering the world all around you?